Board of Directors, Michael Jones, Deputy General Manager. Before I turn the presentation over to Sylvia and her team, I wanted to provide some context to the information that we're going to share this morning. First, staff with support from our consultant team has conducted a thorough and comprehensive analysis of all of the service disruptions that our customers have experienced since August of 2025. I want to definitively state that staff has not identified a single cause of the disruptions. Said differently, there is no smoking gun to share this morning. However, we have extensively evaluated all possible causes that could have contributed to these events. We focused on all aspects of our railroad, including our traction power system, our wayside equipment, as well as our rolling stock. I am confident that as we present our findings, it will be clear that we evaluated everything that we possibly could to get to root cause. We will also share the mitigation efforts, both completed and ongoing, that should provide confidence to the board and the public that we continue to operate a safe, reliable, and efficient transit system. Lastly, I want to address several misconceptions that staff has heard recently from the public and members of the BART board. First, there is speculation that BART leadership has intel on the single root cause of these incidents, but we are not sharing it. This is false. Second, there's a suggestion that blown insulators are the root cause of service disruptions. This is also false. I want to point out that blown insulators are a common occurrence on electrified railroads. It happens, and while it can cause arcing, it has not presented a dangerous condition to cause alarm. We have contacted several transit properties around the country, and we are not unique in experiencing blown insulators, and our maintenance and mitigation standards are in line with those agencies. We will discuss this in more detail during the presentation. Third, there is speculation that this effort did not require the assistance of external consultants and that the consultants don't have the expertise necessary to assist in resolving our challenges. I can assure you that the team we assembled exceeds the expertise of our in-house staff. They are credentialed professionals from global firms that have decades of experience in assistant transit agencies in tackling the issues that we are facing. With this context, I'll turn it over to Sylvia Lamb, AGM of Infrastructure Delivery. But before I do, I want to point out that we have our entire maintenance and infrastructure leadership team here in the room, and I'd like them to stand and be recognized. So these are the individuals that respond to the 1 a.m. calls, the 4 a.m. calls when we have these incidents, and they are responding with their frontline workforce and mitigating these issues. So these are the people behind the challenges that we're having, and I can guarantee you that they are totally committed to making sure that we move this forward in a positive direction. So with that, Ms. Lamb, I'll turn it over to you.
Thank you, Michael. I'd like to acknowledge also that Parsons was the lead firm in this effort for the root cause analysis, and Ebro Muftik, as well as Lori Colangelo with Parsons, is in the audience. And to my left is Zara Younisi. And Zara, while there were tons of experts involved in this investigation, working for Parsons, multiple subs, probably 50 individuals engaged. Zara is one of those experts. She's a California PE. She's also the chief engineer for 3VI, which is a subconsultant to Parsons. She's worked in the UK and the US. She's worked for London Underground. She's worked on BART systems before as far as traction power systems. She's also worked on issues for BART related to the track engineering, and so she's very familiar with our system. As she came in, she's also for other agencies worked at WMATA, again, London Underground, other places in the US, and she also has experience with CBTC. So her credentials are long and wide, and I'm only touching a small bit of it, but we're happy to have her here, and she's going to serve as the collaborant, the kind of focal point of all the expertise that was on the project. So to get started, I want to talk a little bit about the scope of this investigation. As you can see in the middle, we really focused on the area between West Oakland and Civic Center. So that's not to say that if an incident popped up that we didn't also include that into just to check and see if it was something holistic that was also added to this. We did do that, but from a root cause analysis perspective and a scoping perspective, it was really important for us to stay focused and not like kind of trace a thread down. And an example of that is there was an incident in Lake Merritt. That was incident number 3 during this period of time. We did go there and find that it was specifically a rod that had fallen from the ceiling and landed, which had caused that incident. So I just wanted to make sure that we had a understanding of what that scope was. And the time frame, we started, we looked at incidents in August, starting with August 29th. But if something pops up today, the team will go out there and look at that as well. It's not over. This is ongoing investigation, and we're continuing to look at any incidents that come up within our trackway. We followed a very scientific approach to this. That means that it had to be super methodical. And again, trying to get down to a root cause analysis is not an easy thing in a very complex system. It's a high voltage system. It's not unusual to see arcing or sparks on our system. So, you know, it was really important that we stay focused and keep a methodical approach to that. And that started with collecting data. That meant our data from, you know, that we have in-house as far as designs, as far as maintenance records, as far as other work that was going on, but also the very first thing that was done is for a whole slew of people to go to these incidents physically and look at them, and that's part of that collection of the data. So the process went through collecting the data and then analyzing the data and then getting down to some hypotheses. A fishbone diagram is simply a graphical representation that helps a team, after collecting a whole bunch of data, to kind of break down and trace through for root cause. It's looking for cause and effect. It's a common diagram that's used in lean practices, different quality practices. So this is a standard industry in order to do these types of investigations. And, you know, I'm not going to go through every single one of these, but it kind of gives you an idea of the extent of how the team went through to analyze root cause. You know, Michael said it, he kind of stole my thunder there about saying that this was a very thorough and comprehensive investigation and report, and again, ongoing. You can look at the amount of man hours that was put on, the amount of field visits. So site visits, we were in the tube, you know, 37 site visits, but that's not just to the tube. We did go to Lake Merritt, we went to other places, and that's not just the Parsons team. So the consultant team had, like I said, about 50 individuals engaged throughout this process, but we were all hands on deck. And those, you know, the folks that stood up in the back are not the only folks that are involved in this. There's actually more folks in there that didn't stand up. I was going to tell them to stand up, but that's okay. We have tons of people that have been involved. Those 37 site visits, probably, I would say at least 15 of them involved going out in the middle of the night. And sometimes that involved going out, working all day here, going through files of data, and then going out and leaving this office, taking a break for a couple hours, and then going to the site and going out into Graveyard with the power off to really investigate that. A huge part of this, too, going through the bottom right, is the amount of documentation that was reviewed and requested by Parsons and by the consultant team. And it's not unusual when you bring a consultant in, they're coming in cold. The first thing they want to know is all this information. Where is this? Where is this? Where is it? You know, and sometimes it can be frustrating. I'll make sure your mic's on. Sometimes it can be frustrating for the BART team because we want to get going, right? And there has to be a combination of that because the team needs to have all that information.
That's correct. The Parsons team did submit over 100 RFIs within three to 4 days, and we'd like to take a moment to thank BART M&E for the very fast turnaround on those RFI responses. Some were same day, if not same day, next day, so we do appreciate that.
Yeah, so there's a huge amount of data, and all the BART team was very supportive as far as, again, maintenance records, engineering records, everything that we could do. And the whole team knew that this was a top priority to get this investigation done and figure out what's happening in our system. So as far as when we get through the fishbone diagram, and I'll let Zara talk about the kind of hypotheses, but before she does, I want to just say, kind of again to Michael's point, that other than the Lake Merritt incident where we do know it was one rod that fell, every other incident has a combination of factors. It's not one single thing, and there's not one single thing that happened for all incidents, correct, Zara?
That is correct, yes. So this slide here represents the main group of hypotheses put together by the Parsons team. And in some cases, the incidents are straightforward, where there may be one or two causal factors. In a few of the incidents, they're actually more complicated, and it requires a detailed analysis to determine which one is actually the root cause. This represents a very comprehensive look at the system, as well as the subsystems and external factors, and also human factors. Thank you.
Thanks. So let me start with re-describing our traction power system. And you may remember when Miat was here a couple of months ago to give an overview of our whole traction power system. But I think it's really important before we get started today to talk about how our system works and kind of walk through that. Also, I want to point out is that at the end of this presentation, I think there's like 2.5 pages worth of glossary. It's really hard for us sometimes to figure out how to not use the terms that we're always using. So we wanted to include a glossary so that would help. So anyway, our power, as you know, comes from the utility. It comes in at 115 kVAC. The utility is we then step that down to 34.5 kVAC. And you hear that a lot, right? When we come and ask you for approval for a cable replacement, those are our redundant left and right cables throughout the system. That feeds into our substations. At the substation, it's more complicated than I'm going to describe it, but from a simple perspective, it's taking the AC, it's changing it to DC, and it's stepping it down to 1,000 volts. And that is used to power the third rail. So that is a connection from the substation to the third rail that gets the 1,000 volts out there. The rail cars have a collector shoe assembly, which means there's a paddle that rides along that third rail. And as it's riding along the third rail, it's pulling power to help it go forward and also to power the auxiliary systems within the train itself. When you're moving a train and the wheels are turning and there's different heat, there's also current being generated. That current is needs to go back to the substation. So if you follow the orange lines around, it's really important that we close the loop in any kind of electrical environment. So the paddle is pulling power from the third rail. It's moving the train forward. It's powering the inside, all the equipment inside of there. And then the wheels and the different heat are generating current. And that current goes back out through the wheels along the running rails to a negative return shunt. And that shunt has a cable that goes back to the substation. And again, that kind of closes the loop of our circuit with our trains. Also, in addition to that, we have regenerative braking. If you have electrical vehicles, you already know what regenerative braking is, but for us, I'm just going to describe it. Where the negative return current goes through the wheels back through the running rail, as a train brakes, that excess power, it goes back out through the paddle onto the third rail. And this allows any other trains within the vicinity to pull that power from that excess power as opposed to pulling it from the substation again, which makes us more efficient. This is exactly the same as it was in our legacy cars as it is in our cars today. So as we go through this, it really requires a lot of integration as far as this discussion. We can't just look at one thing in a bubble and say that's it or that's not it. We have to look at how all these things integrate together. And you probably remember from the CVTC presentation how important that systems integration is. So as Zara goes through the rest of these slides, she's going to talk about not just these individual pieces, but also how do they relate to each other. And so with that, I'm going to turn it over to Zara to talk about the very first piece.
Thank you very much. So we'll start with traction power and looking at some of the findings and the analysis. What we're looking at on this slide is a rough representation of the traction power substation configuration in the vicinity of the Transbay Tube. The green icons represent the traction power substations that are in service. Originally, and so we're going to start with looking at the design intent. In the original design, there are two traction power substations. On the west side in San Francisco, there is MTW, and it is capable of providing 10 megawatts. And on the East Bay, it's matched by KTE, which is shown in gray. That's the gray icon, because it's undergoing a planned upgrade. To facilitate that upgrade, BART introduced a portable substation known as KPS. We looked extensively at the dynamics of this and the records, and it was determined that this portable substation has been used elsewhere successfully on the system. It is interesting that it has a 5 megawatt rectifier, and it's supplied by a 3.2 MVA transformer. And so therefore the overall capacity is noted on the diagram to be 3 megawatts. Typically on the BART traction power substation, they are 5 megawatts, typically give or take, and they're maybe 1 to 2 miles apart. So what was interesting here is while we originally had a 10 megawatt to the west and a 10 megawatt to the east, that has dropped down to a 3 megawatt. So this is the only place on the system where there is a delta of 7 megawatts. This is being analyzed in terms of what's happening with the power flow. Does it lead to an unbalance? Is there a circulating current, for instance? These are some of the hypotheses that have been bounced around. And in addition to that, to be able to evaluate that further, that is happening through modeling. I would like to also point out that through our review of the records, this change happened in 2021. So it has been operating in this way for about 4 to 5 years, and therefore it's not considered to be the root cause. However, we're looking at whether any of these small changes have moved the needle in terms of the power quality.
Yeah, and Zara said it, but I just want to repeat, that KTE, that gray substation, it is out of service because we had planned for a couple of years before that to upgrade that substation. So it was a planned out of service, and we were waiting for, well, not waiting, but when the portable substation was also available, it was all planned to be done this way.
Thank you. So another finding and design change that we came across through our review. Now, this occurred through site inspections, and I'd like to take a moment to thank the BART structures crew and BART maintenance for supporting these requests. They were through the night, back to back. I personally did go out and walk the track as well to perform these inspections. And through these inspections, we were able to verify that during the dates of the incidents between August and October, the crossbonds were not in place. Now, there should have been 10 crossbonds in place between the Transbay tubes. So what we're looking at on the slide is the purple line represents the crossbond. It's essentially a cable that connects between two tracks. It helps provide additional paths for the return current to flow back to the substation through both tracks. And when, upon our further request for information, we determined that they were removed to support a single tracking project in 2020. And one finding is that upon completion of that project, the crossbonds were not reinstalled. However, they have since been reinstalled.
Thank you.
Oh, I should add also that because this happened in 2020 and it ran in that configuration for about 4 to 5 years, again, this is not considered to be the root cause, but taken together with the previous finding and then this as well, we're looking at the cumulative impact. So this is being analyzed through load flow modeling.
Yeah, and we did, since you added more, we did talk through why would those crossbonds have been removed during the 2020 project. And you may have remembered from the beginning when I said negative return is going back through those running rails. So those crossbonds connect all the rails together. So there was a concern from the team working on that one set of tracks while we were single tracking on the other set of tracks that there may be a potential for, feeling that current. There are other ways to make sure that doesn't happen, and so this was, I think, put in place as kind of an extra measure just to make sure that those two tracks were isolated.
In order to take a closer look at what might be happening on the power system, the Parsons team did recommend installing the power quality monitors. On the top left, you'll see a photo of an actual PQA from this investigation, PQA being Power Quality Analyzer. These are also known as data loggers. The load monitoring tests were performed to look at the incoming power quality, so looking closely at the incoming currents and the incoming voltage into that substation, as well as recording any harmonics. If you're not familiar with the term harmonics, you can think of them as unwanted frequencies. Now, harmonics are not really of interest to us on the DC side, however, they are on the AC side, but they could result in unwanted frequencies on the DC side and a change in the DC ripple. So I should also explain what we mean by DC ripple. So on a typical substation that has a 1,000-volt DC output, much like a DC battery, you'd expect that to be a constant voltage. But in practice, it does come with a small amount of ripple. That ripple is normal. These are 12-pulse rectifiers. And through the process to take AC and rectify it, it's never possible to completely eliminate that ripple. So on a 12-pulse, it's a 720 hertz ripple. And what we were looking at is, did that increase with all of the minor changes here and there? Did that DC ripple look different? And there are additional loggers. Bart took some proactive measures before the Parsons team started to install DC loggers. So similar to the AC loggers that were installed through this investigation, there were DC loggers looking at the output of the substations. The power quality analyzers that were installed were to look at the AC side coming in. So that gives our team a complete picture, and that data is currently being analyzed. In fact, those power quality analyzers are still in place at the MTW substation. They were installed on the East Bay side at KPS and on the West Bay side at MTW. And what was very interesting is that MTW, the incoming voltage, was higher than expected. And if you can squint enough, you might be able to see that on the A phase, it was 815 volts, and then 810 on the B and the C phase. So this is not the 34.5 coming in, because the loggers were installed on the secondary side of the transformer, in between the transformer and the rectifier. So that line-to-line voltage should be 783. So that's how we know it's higher. And when we account for the turns ratio, we calculate that back, and we were able to determine that basically what that means is, instead of 34.5 coming in, it's closer to 35.5 kV on the B and C phase and 36 kV on the A phase. So overall, though, this is really a change of about less than 5%, which is considered to be a tolerable limit. What we are currently looking at is, what were the harmonics associated with that, and did they result in any unwanted frequencies on that DC side that perhaps the vehicles cannot tolerate. The vehicles are equipped with line filters, so they are designed to handle these types of variations, but the analysis requires a further look in terms of modeling and calculation to actually quantify that value. There are also standards that govern this. The EN standards and the IEC standards look particularly at electromagnetic compatibility and immunity limits for these systems, and that is also part of the analysis that's being performed by this team.
Yeah, and so just to kind of recap, one of the things that Zara said is some fluctuation is expected, and in most cases, I think you've said within 5% is tolerable. As long as, I think if it's not sustained, right? Like a sustained ripple could be more problematic, but also something that we have for next steps and opportunities for improvements. Right now, in order to do this, Maintenance has to go out and put a logger there physically. So it's kind of a snapshot in time while that logger's there. So outside of that time, we're not sure when that's going up or down. And so looking for remote monitoring tools that would allow us to do this logging in real time moving forward is one of our recommendations.
Thank you. And with the hypothesis that the small incremental changes may have led to an increase in that DC ripple, the BART data loggers were looked at, and the output did seem to be consistent with DC ripple outside of the normal limits, but that does not mean that they are outside of the tolerable limits, and that's why the calculations are necessary. So in addition to that, now we'll talk more about the negative return and the grounding and bonding. So again, thanks to the BART Structures team and BART M&E, the inspections were facilitated through the Transbay Tube to field verify all of the negative return cables. And we talked briefly about the cross bonds, so I won't repeat that. But there were also some electrical tests performed, and what we can see there in the lower left corner is a fluke meter, just looking at the resistance in particular, this time between the running rail and the track slab. And in two places along the tunnel, that resistance was low. We don't expect it to be low. We want the running rail to be insulated from the track slab. There were further tests performed, in particular looking at the negative grounding devices. So if anyone's not familiar with the negative grounding device, the running rails on BART can have the rail potential can increase to a slightly higher voltage, and once it reaches a specific set point, those NGDs will fire and ground that running rail. It is a safety device. So the NGD at Powell was found to be shorted. That was taken care of by the BART team. And after that, we did see an overall improvement in those resistance values. So moving on to the third rail insulators, these were looked at extensively, including wayside inspections and off-site inspections. A number of insulators were taken to an off-site lab. They are pictured in the bottom right in various conditions, several as found and 2 new. The tests that were performed in 2 different labs actually included destructive testing and non-destructive testing. Some of the observations in the lab, including the forensic testing that was performed, the surface layer of dirt on some of those insulators was found to be conductive, at least on the ones that were tested in the lab, and the shims, which are the thin layers of material that sit beneath the insulators, they help adjust the height of the insulators. They were found to be damp. But overall, the insulator condition is consistent with normal aging and the environmental exposure expected within the tunnel installation. These findings are still not considered to be the root cause, because with looking at the specific incidents and all of the factors, there appear to be other factors that may have initiated some of these insulator failures. And it's also worth noting that not all of the incidents included insulator failures. So another finding, which we'll touch on later, is rail relay storage practices.
So, if you don't mind, let me just jump in one real quickly on the insulators, just to follow up from the earlier conversation. So there's also been news reports that we are cleaning the insulators, and that's partially true. We have cleaned all of our insulators from Embarcadero to 24th and Mission. We did that primarily because we've had incidents in this area, which we're focusing on the root cause now. But it takes a crew of 8 overnight to do 20 insulators. We have over 100,000 insulators, and there's varying degrees of insulator maintenance across the industry. So I want to put out there and clarify that we are not planning to clean all 100,000+ of insulators, but we have taken care of this area just to make sure that we have done everything that we possibly can to mitigate the challenges that we were having on the M line. So, sorry, Zara.
No, thank you. Right, well, let's maybe go back one slide just to point out that the team has got extensive experience in analysing insulator failures and being able to determine whether that insulator was the initiating cause. So we will provide an example of that on the next slide. So this is from one of the incidents, and this is how we're able to, for example, determine if the insulator was the root cause or not. So what we're looking at on the red and black line represents the cover board, and the thicker grey block beneath it represents the third rail. So it's as if you're standing in front and facing this third rail. The white rectangles with the blue underneath represent undamaged insulators, and the red represent damaged insulators. In this case, we'll start with the yellow oval. There was damage noted to the top of the cover board that would be consistent with that damage occurring from the top down, from an initiating source. And we also can see here, when insulator fails, there is a characteristic soot deposition pattern behind that insulator, usually aligned with it. Not always, but in this case, we did see it at the location A, and we did see it at location C. Now, we do also have a team of fire life safety experts on this panel that have been involved in this review. And what's interesting too is that at C, it does tail left in the direction of travel. But the most interesting finding is that pattern did not exist behind insulator B. It was nowhere to be found. The wall was relatively clean, the tunnel wall. But what was interesting is it was projected downwards onto the track slab and in the direction of travel. So the hypothesis that's under evaluation right now is that insulator B did not fail on its own. It was an initiating event from above, a DC arcing event. And we'll look at some of the actual photos from this incident. So once A, then B would have failed in quick succession, as well as C. We're still evaluating A. So this is under analysis to determine if that initiating source was at play as well at the location of insulator A. So on the top right is a photo of the cover board that I mentioned, and there is a stepped profile on the top of that cover board where it's evident, based on this evidence, that the damage was from the top down. And it also aligns with the area of the material loss in the third rail. So for third rail to have essentially a hole in it of that size, that is typically due to high energy arcing. That would be the type of energy required to essentially vaporize that metal in that location, and that's that beneath it is the remnants of the insulator, and you can see that soot deposition pattern on the track slab. And also to the left is how it looks on C, where it's directly behind where the insulator stood.
I wanted to add here, just to, again, give kind of a level of the effort that was put. Not only, was this kind of detail looked at, but even that, when you see that splatter behind it on the wall, scrapings were taken of that and sent to a forensic lab to determine what materials that was as part of the investigation, just to give you a little bit more context on how detailed and how thorough the investigation has been.
So in addition, just to be very thorough, the team also looked at the protection scheme. And the third rail is protected by DC breakers, much like the breakers you'd find in your home panel, except these are DC and much larger. And they can act very quickly to trip and isolate faults. The review of the records revealed that, in fact, so typically the DC breakers all have an ability to trip without an MPR. The MPR is a multi-function relay device that helps customize some settings. We can think of it as an additional layer of protection. When, based on the review of the records, these functions have been disabled. during the time of the incidents. Now, that does not mean that the breakers did not have the ability to trip, because they do have a trip mechanism, but it is more basic, and it would have relied on that basic mechanism. So further RFIs were submitted, and we asked why they were disabled. And the reason that was provided is that they were nuisance tripping in the morning upon return to service. Perhaps Sylvia might want to weigh in.
Yeah, well, there was apparently nuisance tripping, which impacted being able to run cars in the morning, like consistently every morning. And so we found that they disabled these in order to make sure that trains were running smoothly. I also want to add, though, this one has been replaced, and you see the old one versus the new one, although to me they don't look a whole lot different. But our MPRs in our system have been aging, and a lot of them are within 20, 25 years old. We do have a project, and we have had an ongoing project to replace MPRs. So we're about 60% done with that. It's a $22 million funded project. It should be completed within the next 18 months to 24 months. But this area had not been done at this time.
So moving on to vehicles, and this team does include vehicle specialists and SMEs from actually all over the world. And what we're looking at, we'll start with the collector shoe assembly. On the top left, there is an image of a typical collector shoe assembly, and the bottom left shows its position on the vehicle. And then in the bottom right, it's a close-up view of the collector shoe and the braid and the fuse. So we will talk more about this on the next slide, but I just wanted to give you an overview of where it's actually located. So, okay, four of those collector assemblies from the instance were taken to an off-site lab for forensic testing.
Next slide. There you go.
In addition to that, 4 fuses were provided to the Parsons team by the BART vehicles team. These fuses appeared to exhibit a non-standard failure, and they were taken to a lab for further testing, including forensic testing. So fuses, much like the fuses that you find in your home appliances, have a fusible link that will melt if the current exceeds that threshold. And these fuses are different because they're slightly larger, but they also do include that fusible link. But they also have quenching sand that helps extinguish that arc at that point. So when that fuse typically fails, that we'd expect that sand to turn black. But in this case, the sand remained white. And we can see extensive damage to the exterior of the fuse body, also known as carbonization. The tests were extensive, including an elemental analyzer test on the area that looks like brass. It was confirmed to be brass. So those pins are actually zinc or zinc plated. And it was interesting that brass was found there. That is, for brass to form with zinc, we need copper and an extremely high temperature. So it's yet to be confirmed, but the hypothesis is that there was high energy arcing in that area. In addition to that, there are other signs looking at the lug. So if you're not familiar with the lug on the top right, we pointed to the braid on the previous slide. The braid is connected to the fuse, and that rectangular piece that's coming in on an angle.
With the 2 holes.
With the 2 holes, thank you.
Sure.
That also has material loss. You can see that there's a kink in it. It's not designed that way, so that is another sign that there was perhaps high energy arcing at that point. And more evidence of that was looking closely at the inside of the end cap where there is beading. And that's basically those tiny little metal balls that you can see there that would be indicative of perhaps a high energy, maybe a thermal event or arcing within the end cap, and it may have come from the lug itself. However, this is still under analysis. Further testing is recommended on the fuses, and we will have additional updates on that in the report.
Yeah, and so on the quenching sand in this kind of event, Zara, you're expecting to see that sand be black, right, instead of
Correct.
the white, right? Okay, next slide, Bob. I'll start with the rail storage. Zara brought it up a minute ago briefly, but at BART, the maintenance practice for years and years, I don't even know, like forever, has been to do our rail in 800-foot sections. And I noticed before, or when talking to one of the directors about rail relay, so let me just explain. The term rail relay just means replacing the rail. That's our projects that we do all over the place. But given the short windows of maintenance windows during the blanket, that 3 hours where the power is off, it takes a long time to get that rail moved out to the right section and then to do the work. So what the practice has been is to bring rail out and place it wayside either in between the third rail and the running rail, or in between the two running rails. And then at a later time, when we're doing the actual project where BART maintenance will go out when we have single tracking or weekend shutdown, and then replace the rail. They leave the old rail there, and then over the next period of time, come out during the blankets and pick that rail up, or break it in. They cut it into sections and then take it out. But so what the team saw, and now I'll turn over to Zara.
Thank you, Sylvia. So as part of the analysis on track, one of the findings was a non-standard practice to store ribbon rail in the gap between the running rail and the third rail. And in fact, to accommodate that, it does appear that the cantilever brackets were cut back. So in that top right photo, you can see an example of that where there is really like a diagonal, where you see that diagonal cut. That was cut back to accommodate this. So why is this important? Well, there was one event that did appear to include the ribbon rail, or involved the ribbon rail. There was evidence of arcing found on that ribbon rail itself. So, yeah.
And since the investigation, all that rail's been removed in this area, by the way. So, and then you want to talk about the insulated joints.
Insulated joints were also carefully looked at. So, insulated joints are a normal part of the BART infrastructure. They're typically used to help with the detection of trains. And negative return current has got to go around those IJ locations. That's typically facilitated by little jumpers that go around the IJ. These are insulated joints of current. The DC return current cannot pass through them without going around. What we had noticed is that in support of the earlier project that was mentioned, IJs were installed at the locations shown on that graphic. So to picture an IJ, there's a photo of that captioned, and the graphic is showing the green rectangles as the IJs that were installed to support those projects, and the purple was also green at one time. So during the investigation, it was determined that through the rail relay work that was done on the M2 track, so basically a new length of running rail was installed on the M2 track on 1012, and that IJ was removed. And then 2 weeks later, the other side, that running rail on the other side was removed, was installed, and then that IJ was removed. So basically, for a period of 2 weeks, there was a different operating condition in play for at least two of the incidents. So that too is being analysed, and again, it requires modelling to fully determine what the impacts are of this.
Thanks. Next slide.
Finally, just to be thorough, there was a huge effort to look at environmental factors and human and external factors. So, I mean, the slides I think are self-explanatory, but there is evidence of water intrusion in places. During one of the inspections, our team also noticed there was standing water in the Transbay tube, but only a small area, and we submitted an RFI, and that was confirmed to be due to a sump pump, broken sump pump that's since been repaired. Generally, there's debris, as you can see, throughout the platform areas and the tunnel, and rail grinding as well, which I believe Shane can speak more to that on the rail grinding practices, because there are there are good measures in place to minimize that. So overall, because these incidents did happen in the TBT, the environmental factors will probably remain as one of the contributing factors, but not necessarily the root cause.
Next slide.
So the final area is the interface, and the interface is basically where all disciplines come together, and this is where we have basically the interaction of the shoe and the third rail. The team has looked at extensive data, including the geocar data, looking at track defects in particular and their locations. The team also performed a third rail gapping study, which confirms the location of third rail gaps. And one of the hypotheses is the possibility of a shoe bounce or a quality of contact issue where a DC arc might momentarily form, but if it does form, perhaps it's being sustained, and we're looking into this as a possibility. But while we are looking at this, it is also important to remember that a small amount of arcing is also normal and on major, DC electrified third rail transit systems. It's momentary, it's not expected to be a sustained arc. But once a DC arc does form, it is very difficult to break that arc.
Next slide. These are all the improvements that have been implemented while the root cause analysis team has been working on the investigation. So I just want to mention that the first one up there is that there was a, not our structure, but San Francisco, at the San Francisco transition structure, there were 2 transformers that had been out of service, one from I think December of 2024, and then one in February, and that's been since put back in place. But all the ones with check marks are the work that maintenance has been doing to, for instance, restore the cross bonds, clean up debris, do, as Michael mentioned, cleaning the insulators, and also looking at the repairs of the negative return device. That one short was repaired, but we're looking at all the other devices as well, and looking at which ones need to be prioritized to be repaired or replaced. There is already a project for that, for maintenance to do that replacement. RSNS is working on further testing and looking at different things with vehicles. So there has been a lot that's gone on. Like I said, maintenance has removed that ribbon rail, and also been replacing direct fixation pads, which were found to also be degraded and also had some moisture. And again, that's a project that's being done by maintenance. Next slide. Do you want to talk about these? So in each, I'll talk about that. So we said in the beginning that for each incident, it was most likely multiple things that had caused those incidents. And there wasn't, even though we're kind of combining these into categories, there wasn't like one thing that affected every single incident. So this is just kind of a breakdown of the incidents that happened and what were the potential causes related to that. Again, except for incident 3, where we know that there was a rod that fell from the ceiling that had that impact. Next slide. And next steps, before I get started, I just want to say the picture on the right is not the BART system. It's a, it's a picture from the rail inspection vehicle software to use for display purposes. But the next steps, there's a couple of big ones. So first is finish the modeling that the consultant is doing of this area. They are putting in every single piece of equipment, everything in the system, just everything having to do with that. There's a couple things that are good with that. One, it's going to help us run different scenarios to validate the causes that we think about, that we've come up with, or the team has come up with, and then also be able to run scenarios to see if we can recreate that explosion arcing digitally as opposed to physically. We're also looking at opportunities to better maintain our insulators, whether that means looking at different designs and materials that are being used nationally. We've already been in touch with many other agencies on their cleaning practices, as well as the type of insulators that they use. And then Zara mentioned for the vehicles, we're conducting some additional vibration studies and tests on the collector shoes. And then for policies and procedures, working with safety, I think between safety and maintenance to develop a configuration control type document and procedures so that when certain changes are made in the system, they are signed off. Like that everybody knows that that's happened and they all agree to why it happened. And in that document or in that procedure, also what is the date for that to be put back the way that it should be. So I think that's something that's definitely an opportunity for us. And then I mentioned earlier about having constant, continual remote monitoring and logging tools. I want to note, and one of the reasons that we added the picture to the right, you guys, most people are familiar with our rail inspection vehicle. We use that for mostly, we've been using it mostly for track, looking at track defects and needs there. Just this week, we've started running it with power on to use that vehicle to look for any kind of heat anomalies or any kind of power anomalies in those areas. So that's, I think they've done 2 runs this week. So that's also something that we'll evaluate, the data that we're getting from there and how helpful that will be in the future. And with the modeling, depending on how it turns out and what we're able to do, it may be something that we want to expand to other pieces and the other places in the system, again, to help identify and be proactive about any potential vulnerabilities. And with that, next slide, we will take questions.